like, what is the paradigm here? Basically, we made the uniform superposition on all the qubits. Then we did if this mystery bitmask XOR function, then minus. Then we did the Hadamard transform. And then we printed. Okay, so it followed that paradigm introduced in lecture 6. Now, we didn't prove it or anything, but we sort of saw in the demo that the result of running this code was that it, 100% of the time, printed out in this case, 100% of the time, it would print out 101110. So it would seem, therefore, if that's the case, it would seem, therefore, that right before the extract all, it must be that all of the amplitude is on, this basic state, 101110. Maybe it could be have amplitude -1 on this and amplitude 0 on everything else. It turns out it actually has amplitude +1 on this and amplitude 0 on everything else. Because that's the only way you get in the situation where 100% of the time it will print this string. So, what I'm saying here is that evidently it would seem that, and we will prove this, but evidently it would seem that, let me write it so it's clear. So seemingly, if you start a state with amplitudes being the ±1 truth table of some bitmasked XOR function, and then you do the Hadamard transform, the result is just all amplitude on this basic state. Because that's what we did here. Effectively, by doing this operation and this operation, we loaded the truth table, but in ±1 notation. We loaded the ±1 notation truth table of this function into the state. Then we did the Hadamard transform. Then apparently, all the amplitude was just on this one basic state. So remember at the beginning of the class, I told you, okay, today's lecture, we're going to find out in general, if you have some state of n qubits, and then you do the Hadamard transform, how do you understand what the resulting amplitudes are? And once we understand that, one thing we'll come to realize is indeed exactly this. One feature is that if the original state happened to be the ±1 notation truth table of a bitmasked XOR function, and then you do Hadamard transform, then you get all the amplitude on this one string. Okay, so now I will just directly tell you the theorem statement about what happens when you do the Hadamard transform. And then we'll prove that theorem statement. Okay, so the theorem. Suppose the state of n qubits is the ±1 truth table of some Boolean function f with n input bits and one output bit. In other words, the state is what you would get if you first made the uniform superposition and then you did if f then minus. And then you do this Hadamard transform, which means in quantum notation average and deviation all. Then I should tell you what the new state is, so I'll tell you what all the amplitudes are. The resulting amplitude on any given basic state, b1, b2, dot, 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 bn, is the correlation, which I will define this term, it's the correlation of f and the function XOR sub b1, b2, dot, 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 bn. So that's the theorem statement. So you load in the f's truth table, do the Hadamard transform, then you get 2 to the n numbers, all the new amplitudes. And those 2 to the n numbers encode the correlation, which I'll define in a second, of the function f with all the 2 to the n different bit-masked XOR functions. All those correlations are like the new amplitudes. But, you know, if you take an intuitive meaning, I'll define in 2 seconds, of like what correlation means, then you should, you know, this should resolve this seemingly in your mind. Because like in this case, we imagine starting with f, which itself was some bit-masked XOR function. So then, based on your intuitive notion of what correlation should mean, it should maybe seem quite likely that this is the state that has only, you know, that the resulting, sorry, this is the state that has like, you know, amplitude 1 on this and amplitude 0 on all other basic states. So this is kind of telling us, in particular, that like the resulting amplitude on the B string, which happens to be this bit mask, is 1. That's like sort of full correlation, because indeed f is this function. And moreover, actually, all the other, it has like no correlation with any other bit masked XOR function. Maybe that's less intuitive, but like, it should make sense that we get a like full correlation on this XOR function. Okay, well, in order for that to make sense, I should give you the mathematical definition of this correlation. Okay, so the correlation of 2 Boolean functions f and g, let's say that are both mapping n bits to 1 bit, is, I'm going to call it is, I'll use this notation, core f g. It's a number, and it's the fraction of inputs x where f and g agree, minus the fraction where they disagree. Okay, so it's the difference of 2 fractions. These 2 fractions add up to 1 as well, right? I mean, it's the fraction where they agree minus the fraction where they disagree. So let's do some facts about this quantity. You know, so to compute the correlation between f and g, like imagine you're looking at the truth tables of f and g, and you look at all the rows and see like how many times they agree and how many times they disagree, and you convert those to fractions, and then you subtract. So this correlation between f and g is a number between -1 and 1. And it's 1, which is like full correlation, if and only if f and g are the same function. Right? And if f and g are the same function, they agree on all the x's. That's fraction 1 where they agree, fraction 0 where they disagree. So it's like 1 minus 0 is 1. Conversely, like the correlation between like f and g is -1 if they like maximally disagree, which is like if f of x is always like the negation, you know, the not of g of x. Then the fraction where they agree is 0. The fraction where they disagree is 1. So 0 minus 1 is -1. What does it mean if correlation of f and g is 0? Well, it means they agree on half the inputs. half of all 2 to the n inputs. Okay, because then the fraction where they disagree is also a half, and like the difference of a half and a half is 0. These are not all the possibilities. You know, the correlation can be like 0.9, or let's say the correlation can be 0.8 if they agree on 90% of the inputs and they disagree on 10% of the inputs. Then the correlation would be 0.9 minus 0.1, which is 0.8. I guess it's not possible because 90% of like a power of 2 is not an integer, but don't worry about that. Okay. Any question about that definition? So it's like an interesting thing to know, like what is the correlation between two functions? And it kind of says that, this theorem kind of says that like, if you load f's truth table in plus or minus 1 notation into a state, you do the Hadamard transform, you get out 2 to the n numbers. If you, like as a mathematician, could just look at all those 2 to the n numbers, they'd be telling you simultaneously the correlations of f with every possible bitmasked XOR function. Is that interesting? It's kind of interesting. Okay. Before we do that, let's like just do some more examples or think about this a little bit more before we eventually dive into proving this theorem. So here's a question I want you to think about. This is a bad marker. If I give you some function f, what is the meaning of the correlation of f with this XOR function, XOR sub 0, 0, 0, dot, 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 0? What do you think about that in words? Yeah, tell me intuitively about this quantity. Somebody? Yeah. Yeah, so exactly. It's the fraction of inputs where f's output is 0 minus the fraction where it's 1. So it's kind of measuring how biased f's truth table is to zeros versus ones. So let me repeat that. Recall, I mean, XOR sub 0, 0, 0, 0, we discussed, is the function that's always 0. So like this correlation is about comparing f's truth table with the truth table of all zeros. So you're measuring, right? So this correlation is like the fraction of inputs x where f of x is 0 minus the fraction where it's 1. And indeed, this kind of measures it's a number which measures sort of the biasness in the sense of this bias busting algorithm of f's truth table. So for example, the correlation of f and the XOR with bit mask all zeros is plus 1. Well, if and only if f is the constantly 1 function. No, the constantly 0 function. And it's minus 1 if and only if f is the constantly 1 function. And it's 0 if and only if, well, if and only if these two fractions are both a half. If and only if f is unbiased in the sense of lecture, well, last lecture, if the truth table is 50-50 zeros and ones. But you see also like, if you take the fraction of inputs where f of x is 0 and subtract the fraction of inputs where f is 1, this is kind of like the average over all x of kind of like count the number 1 if f of x equals 0, but count the number minus 1 if f of x equals 1. right? Because if you just average, 1 when f of x is 0 and minus 1 if f of x equals 1, like that'll turn out to be the fraction of inputs where x is 0 minus the fraction where f of x is 1. But this is like equal to the average over x of like, f of x in like plus or minus 1 notation. The notation where like, that you get after if the f then minus, where like minus 1 corresponds to output 1 and plus 1 corresponds to output 0. So by definition, like this quantity is like the average of f's plus or minus 1 truth table values. Okay, so just by definition of correlation and by definition of what is plus or minus 1 truth table, you see the correlation of f with this all zeros bit mask XOR function is the average of f's plus or minus 1 truth table values. And so that fact corresponds to this theorem in the special case where b1 through bn is all zeros. This theorem, like when you plug in the special case where b1 through bn is all zeros, it's saying if you load f's plus or minus truth table into the state, you do the Hadamard transform, and then you just look at the amplitude on all zeros, it's saying you get the correlation of f with the XOR sub all zeros. In other words, you get the average of f's plus or minus 1 truth table values. And that's exactly what we proved last time in lecture 8. That was the special case we proved last time about Hadamard transform. The correlation on all zeros is like the average of the plus or minus 1 truth table entries. So now I guess you're like, great, we've proved this theorem in the special case where b1 through bn is all zeros, just to prove it in every other case. Any questions about this? Yeah. The question was, it's quite clear that if f is itself some XOR function with a certain bit mass b1 through bn, it's quite clear that like that function's correlation with itself is 1. Like the correlation with XOR sub the same bit mask is 1. I mean, that's this fact. But evidently, it would seem, based on our experiments back in lecture 1, that the correlation of XOR sub string b with XOR sub string c for some other string c is 0. Because this thing never printed out anything other than b. So you might wonder, like, why is it true that like if you have the truth table for some masked XOR function and a truth table for some other masked XOR function, is it true that their correlation is 0, that they agree in exactly half of all bit strings? That's not super obvious, but it's actually like a pleasant math problem to work out. It's not completely dissimilar from like the bonus question. And well, it's I think a little bit easier than the bonus question on homework 1. But it is a true fact that two XOR functions that are not the same XOR function agree on half of all inputs and disagree on half of all inputs. If you want to see an extremely indirect, almost like cheating proof of this, I can tell you an indirect cheating proof, which is that this is real cheating, but, well, it's a real proof, but like it's too indirect. We actually know after you run this code, you get back a normalized state because you have just as many add and diffs as average and divs. So you get back a normalized state, for sure. And we know that like if you were to run this where f really is this XOR function, we get back amplitude 1 on the special string b1 through bn. Because it's obvious, I mean, if you believe this, the correlation of f with itself is 1. So we know one of the amplitudes after this has like amplitude 1 on the particular b string that it is. But we know it's also a normalized state, which means the sum of the squares of the amplitudes has to be 1. But we already have amplitude 1, which squared is 1. So there's no room left for any more amplitudes. So that therefore all the other amplitudes have to be 0. Now this is a very, very indirect proof. So that's why I said like it's a bit cheating, but it's interesting. Instead, you should think about it. I mean,